Where's my okay, so these ones are a little bit more difficult. So number one, we have an 85 kg hyperthermic runner with an average temperature of 38 degrees Celsius, who's wrapped in a damp cloth and cooled to a temperature of 36 degrees Celsius. The dominant method of heat loss is via the evaporation of water from the cloth. How much water must have evaporated in kilograms? And we know the specific heat capacity of the body, which is 3,500. And we know the latent heat of evaporation, which is LV. So I'll just quickly go over the phase changes, which I haven't covered. So when you go from liquid to gas, we call that evaporation. So liquid to gas is evaporation. For example, when you go from liquid water into steam, that's evaporation. And at atmospheric temperature, for water, this is going to occur at 100 degrees Celsius. So at 100 degrees Celsius, liquid will start to turn into gas. And this gas will also be at 100 degrees Celsius as soon as it turns into the gas. Okay? So that's important to realize, is that you can have liquid and gas both at the same temperature. Okay? So you can have steam that's 100 degrees Celsius, and you can also have water that's 100 degrees Celsius. And you have to, it requires energy for that liquid to turn into gas, and that energy is quite big, and that's what we call the latent heat. So this is the LV, that's the latent heat of, it's not evaporation, sorry, it's vaporization. Sorry, I had it's the latent heat of vaporization. And latent means that it's kind of hiding, or you can't really see it. So latent, it's latent because the temperature is not changing, but that energy is going into breaking the bonds in order to allow the liquid to turn into gas, right? And that's quite a large value. So if you see here, and another thing to watch out for is that for water, the latent heat of vaporization is 2,415 kilojoules, and remember you have to have your units in joules, so that's 2,415 times 10 to the 3 joules, and that always catches quite a few people out. So it's a really big value. It's a really big value. 2,415,000 joules. Okay. Yeah. Okay. So what we have here, we want to know how much water must have evaporated in order to cool this man from 38 degrees Celsius to 36 degrees Celsius. So we know that our change in temperature is going to be -2 degrees because he's lost heat. So -2 degrees Celsius. And because it's delta T, we don't have to convert that into Kelvin. It's the same as Celsius or Kelvin. And so if we wanted to find out how much water has evaporated, you'd use this equation here. So Q, our heat energy, is equal to the mass times the latent heat. All right. So we want to find out the mass that has, so you use this equation here. This equation here is for when you've had a phase change. So when you've gone from liquid to gas, or liquid to solid, or vice versa, okay? And if they give you the latent heat, then you're going to use this equation. So this is the mass, the amount of mass that has changed phase. So in this case, it's gone from liquid to gas. And so if you rearrange that, that's going to be M is equal to Q over L. Okay? So we know the latent heat of vaporization. We've been told that. So what we need to do is we need to first figure out what Q is going to be. So we can use the equation that we used in our last tutorial, which was Q is equal to MC delta T. So we know how much the temperature of the man has changed by. So the mass of the man is 85 kilos. And we know that the heat capacity of the man is 3,500. And we know that the change in temperature was -2 degrees. Okay, so the change in heat, the amount of energy that the man lost, that will be 595,000 joules. Okay, so remember that whatever the man loses is going to be how much the water gains. So this Q will be equal to the Q of the water. So the mass of water has gained the same amount of energy in order to evaporate. So that means our Q will be 595,000 over the latent heat of vaporization, which is 2,415 kilojoules, so times 10 to the 3. And that's going to be 0.25 kilograms. All right. So what we did is we figured out the amount of energy that the man must have lost, and that's going to be equal to the amount of energy that the water has gained in order to evaporate. So that's what I've done here. Cool. So our second one, we've got a bath which is filled with a mixture of 300 kilograms of water at a temperature of 15 degrees Celsius, 200 kilograms at 5 degrees Celsius, and 100 kilograms at 50 degrees Celsius. After thermal equilibrium is reached, so thermal equilibrium means they're all at the same temperature, right? What's the final temperature of the water in the bath in degrees Celsius? So whenever you have a few objects at different temperatures and they ask you for the final temperature, you're going to use this equation here. So write this one down. The final temperature, TF, is equal to the mass of object 1 times the heat capacity of object 1 times the initial temperature of object 1 plus the mass of object 2, heat capacity of object 2, times the heat capacity of object 2 times the initial temperature of object 2. And in this case there's 3 objects, so we can just keep adding objects as they come. So you can do M3, M4, but usually it'll just be 2 or 3 objects. So M3, C3, T3. Okay. Just remember that you can keep adding as you need to, but usually you won't have to. And that's over M1, C1 plus M2, C2. Okay. So it's basically the same as the top, except on the bottom you don't have the T.
Do we have M3?
Oh yeah, so sorry, you need M3. You need M3, C3 as well. Thanks for catching that. Yeah, so that's your equation, and then all you have to do is put your numbers in. Oh yeah, and for this one, so because this one deals with like changes in temperature, you don't actually have to change the initial temperature into Kelvin. So you can just use your Celsius value here. So you can, for T1, you can just use 15 degrees. So our mass one is going to be 300 kilograms. And, oh, sorry, so here we haven't been told the specific heat capacity of the water, but because they're all the same object, they're all the same material, water, right? So the heat capacity of all of them are going to be the same. So C1 equals C2 equals C3. So that means we can just cancel out all the C's in this instance. And we don't have to have, we don't need to know the heat capacity because they're all just the same, because they're all just water. So 300 times initial temperature of water, the 300 kilograms, which is 15, plus 200 times 5, plus 100 times 50, and that's over 300 plus 200 plus 100, and that's going to give you 17.5 degrees Celsius. Okay, so pretty simple, not too hard, as long as you know this formula and you have it on your cheat sheet. Okay, so I'll move on. We have water boiling in a large pot, and water vapor is being produced at a constant rate. So if water vapor is being produced, it means that we have liquid turning into a gas, right? So there's going to be energy going into breaking those bonds between the liquid water molecules to turn them into gas. In 1 hour, we have 300 grams of water vapor produced. How much power is being used to convert the liquid water into water vapor? And we want that in watts. And they've given us the latent heat of vaporization of water at 100 degrees. So the variable that we're looking for here is P. So P is equal to question mark. Right, so this one's a bit of a hard one initially to kind of figure out how to like solve it. But again, when you're confused, just try and look for the variable that you're looking for, and then look at the equations that you have for that variable, and that should kind of lead you onto the right track. So we're looking for power, right? And if you look at the equations for power, you've got power is equal to energy over time. So we've been given the time. So our time is equal to 1 hour. So 1 hour is 60 times 60, which is 3,600 seconds. So we have our time. So in order to find out our power, we just need to calculate the amount of energy that we've been using. So we can do that because we know the mass of water vapor that has been produced. So we're going to calculate Q. So we can calculate Q by using ml. So Q is equal to the mass times the latent heat. And the mass is going to be 300 grams, which is 0.3 kilograms, times the latent heat of vaporization, which is 2256 times 10 to the 3, and that will give you 676,800 joules. Okay, so that's the amount of heat energy. So remember, Q is a type of energy, which means that you can just substitute it into this equation here as energy. So P is equal to 676,800 divided by the number of seconds, which is 3,600. and that will give you 188 watts. Okay, and remember that watts is joules per second, so we're using 188 joules of energy per second. That's what that means. So it's pretty simple once you know how to do it. The hard part is actually figuring out what to do. Once you know what to do, it's usually just putting in the numbers. Okay, so number 4, which one of the following statements about heat transfer is false? We're going to go through them one by one. Option A, when heat is transferred because of a temperature difference, then the heat flows from the hot object to the cold object. So this is always true. So yeah, hot to cold, that's pretty obvious. And then B, 2 objects allowed to come to thermal equilibrium have the same temperature. That's true. C, heat transfer can take place simultaneously by conduction, convection, and radiation. So that's true. Conduction is heat transfer through contact. So conduction is the transfer of heat through physical contact. So if you're actually touching someone, you're conducting heat. So that's a method of heat transfer. And then your second method of heat transfer is going to be convection. So convection is the heat transfer through the movement of fluid particles. Through the movement of fluid. So, for example, if you have a running tap and then you put your hand, if say your hand was hot or whatever, and you wanted to cool it down, so you put your hand under the tap, a running tap, then the water is moving, right? And those, so water is a fluid, and those fluid particles, water particles are moving along. So the heat is going to be transferred to those water particles, and then they're going to be carried away. So the fluid is carrying away the heat, and so that's what we call convection. So it's pretty similar to conduction, except that in conduction the objects aren't actually moving, right? So it took me a little while to kind of understand it, but you'll understand it more when you cover it in the lecture as well. That probably wasn't the best explanation of it, but it'll do for now. Radiation. So radiation is just radiating energy. So just what heat energy is basically photons. So you guys know what photons are. So photons are like particles, packages of energy. So yeah, whenever, what you're actually doing is, if you look at the atomic level, you're actually shooting out photons, and you're losing photons, which is energy, and that's what radiation is. So through photons. Okay. So that means that C is true, and then so now we'll look at D. So conduction, convection, and radiation can all transfer heat through a vacuum. So D is going to be false, because remember, in order to have conduction, we have to have contact. So if we have a vacuum, there's nothing touching, so we can't have heat transfer through a vacuum by conduction. For convection, we have to have a fluid, so vacuum has nothing in it. So that's false. You can't have heat transfer by convection through a vacuum, but you can have heat transfer by radiation through a vacuum, because remember, photons can travel through a vacuum. right? So D is false. The only thing that can transfer heat through a vacuum is radiation. And then E, the rate of heat transfer by conduction, convection, and radiation all depend on the difference in temperature between two locations. So this is true. You're always going to go from high to low. So you're always going to go from high temperature to low temperature. And the greater the difference, the greater the gradient between those two locations, the greater the amount of heat transfer there's going to be. Again, number 5, a well-insulated container holds 1 kilogram of liquid black tea at 80 degrees Celsius. And we want to cool this to 5 degrees Celsius to make iced tea. How much ice, which is at 0 degrees, would you need to add to the tea in grams? And so you've been given the specific heat of tea and water, and then the latent heat of fusion of water is 334 kilojoules per kilogram, and you've got the melting point of ice. So similar, before I talked about vaporization, which is going from liquid to gas, but this time we have fusion. So fusion is when you go from a solid into a liquid. Right, so we've got ice, which is a solid, turning into liquid water. And we call this fusion, right? Anything going from solid to liquid is fusion, and we're going to have a latent heat of fusion. So LF, that's the amount of energy that's required to break those bonds, the chemical bonds. And so the ice is going to be at 0 degrees Celsius, and the liquid water is also going to be at 0 degrees Celsius. So that's important to realize that. Okay, so when the ice is melting, it's going to be at 0 degrees Celsius, and as soon as it turns into that liquid water, it's going to be at 0 degrees Celsius. So you can have ice and water both at 0 degrees Celsius, and there's energy being used in order to turn that ice into water, and that's why we call it the latent heat, because there's energy going in, but the temperature isn't changing. All that's happening is the solid's going to a liquid, and that's why we call it the latent heat, which means you can't see where the heat's going. Or looks like the energy's disappearing, but it's not. Okay, so this one's a bit of a hard one. And remember that, so I'll just drop this off now because I'm going to need the space. So remember that when you have delta T, it's going to be TF minus TI. Okay, so remember that. So we have two objects here. So we have the T and we have the ice. So we're going to treat, these are the two objects in our problem. So the T is going to lose energy, right? Because it's got a high temperature and it's going to come down. It's got to come down to 5 degrees Celsius, whereas the ice is going to gain heat. So you can say the amount of heat that the T gains, that the T loses, plus the amount of heat that the ice gains will be equal to 0. Because remember the amount of energy will be equal. It's just that one will gain it and one will lose it. Sorry, ice will gain the energy and T will lose the energy. So you'd use this equation here. And so the Q for T will be equal to MC delta T, right? Because it's going from 80 degrees Celsius down to 5 degrees. Whereas the Q for ice, there's two components to it. You have ml, because it's going from solid to liquid. And you also have the change in temperature. So after it turns into liquid, it's going to be at 0 degrees Celsius, and you need to increase the temperature to 5 degrees Celsius. So the Q of ice will have two components. It's going to have the phase change and the change in temperature. So then we'll put that into an equation. So Q of T is going to be M, so the mass of T, times the heat capacity of T, times the delta T, which is final temperature. So TF minus the initial temperature, plus the Q of ice. So that's going to be ml, so m, the mass of ice multiplied by the latent heat of fusion, plus the mass of ice multiplied by the specific heat of water multiplied by TF minus TI, which is delta T. Okay? And that's equal to 0. So everyone's keeping up with what I've done here? Is anyone confused? Okay, so I'll move on. So now we're just going to put in our values. So 1 kilogram of T, 1 times specific heat of T, which is 4.18 kilojoules, which is 4,180 joules. And then so TF, final temperature, is going to be 5. Yeah, and so here, for these ones, you don't have to, whenever it's involving delta T, you don't have to convert it into Kelvin. You can just use the Celsius value. So 5 minus the initial value, which was 80, plus the mass of ice, which is which we don't know, so we're going to leave that in our equation. So that's times the latent heat, which is 334,000, plus the mass of ice, which we don't know, so we're going to leave that as m, times the heat capacity of water, which is 4,180, times the final temperature, which is 5, and the initial temperature. So what's the initial temperature of the water going to be? Yep, 0. That's right. And that's all equal to 0. So you're just going to do all the maths. So that's going to be minus 313,500 plus 334,000 m ice plus 20,900 m ice equals 0. So then 354,900 m ice equals 313,500, and m ice is equal to 0.883 kilograms, which is equal to 880 grams. Okay? So quite long, but we got there in the end. Does everyone understand that? Okay. So number 6, we have an 85 kg hypothermic skier with a temperature of 32 degrees Celsius, placed in a well-insulated bath containing 180 kilograms of water at a temperature of 38 degrees Celsius. What's the final equilibrium temperature of the water and skier? So you have two objects at different temperatures, and you want to find out what the final temperature is going to be. So I showed you the equation for this before. It's going to be TF is equal to M1 C1 T1 plus M2 C2 T2, and because we only have two objects, we only need to have 2, and that's over M1 C1 plus M2 C2. Okay, so that's pretty simple. You just put in the numbers. You don't have to convert into Kelvin. So 85 times 3,500 times 32 plus 180 times 4180 times 38, and that's over 85. The mass of the person, 85 times 3,500 plus 180 times 4180, and that will give you 36.3 degrees Celsius. Okay, so number 7, we have a gas cylinder with a volume of 2 meters cubed. It contains 10 moles of nitrogen gas. At a temperature of 15 degrees Celsius. The gas cylinder is heated, which increases the thermal energy of the gas by 30 kilojoules. What is the temperature of the nitrogen in the cylinder now? So we want to know the final temperature. So here we want to find out the final temperature. That's our question mark. And so we'll just write down the variables that we've been given. So we know that our change in the thermal energy, or the change in internal energy of the gas, is equal to 30 kilojoules, which is 30 times 10 to the 3 joules. And we know that the volume is equal to 2 meters cubed. We know that the number of moles is 10. And we know that the initial temperature, so the temperature is going to be 15 degrees Celsius. So 15 plus 273, that's 288.15 Kelvin. Okay, and also we've been told that it's diatomic. Sometimes, they haven't told you that it's diatomic, but you've got N2, so whenever you see that, it's going to be diatomic. So we want to find out the final temperature. So what we can do here is we can use this equation here, delta U. Our change in internal energy is equal to, so this time we're going to use 5 over 2 because it's a diatomic gas, multiplied by the number of moles, multiplied by R, and multiplied by the change in temperature. So we could find out the change in temperature, and then add that to the initial temperature in order to get our final temperature, right? So that's what we're going to do. We're going to rearrange this equation. So then our change in temperature will be equal to our change in internal energy over 5 over 2 times N times R. So that's 30 times 10 to the power of 3 over 5 over 2. So you could just write that as 2.5 if you wanted to, because 5 divided by 2 is 2.5, times the number of moles, which is 10, times our R value, which is 8.3. Okay, and so that should give you so that's 144.6 degrees Celsius. So that's our change in temperature. Oh, so here, sorry, I could have left this in Celsius. So the initial temperature was 15 degrees Celsius. And we have our change in temperature of 144.6. So our final temperature will be equal to the initial temperature plus our change in temperature, which is 15 plus 144.6, and that's going to be 159.6 or 160 degrees Celsius. Yeah, so you might be a bit confused about when to turn into Kelvin and when not to, but as you just keep doing more of these problems, it should you'll kind of understand when you can and when you can't. So number 8, Miles has 500 grams of water at a temperature of 15 degrees Celsius in a kettle. The water will boil at 100 degrees Celsius, and the kettle transfers energy into water at a rate of 750 watts. So we've been given 750 watts, which is power. Okay. How long will it take to boil the kettle dry? And that's in minutes. We've been given the specific heat of water and also the latent heat of vaporization. So we're wanting to know how long it will take for the water. It has to go from, so what's happening here? It's going from liquid at 15 degrees Celsius to liquid at 100 degrees Celsius. So that's going to be, so in order to do that, you need energy. So that's Q equals MC delta T, right? And then once the liquid is at 100 degrees, so we're going from liquid 100 degrees Celsius, and that's turning into water vapor. So that's turning into water vapor at 100 degrees Celsius, and that's going to be the latent heat of vaporization. Okay, so you need to calculate both of these. So that's the total amount of energy that's going to be required. So let's calculate the total amount of energy that's going to be required for all the water to become vapor. So Q total will be equal to MC delta T plus ML. So Q total is, we have 500 grams, which is 0.5 kilograms, times the heat capacity, which is 4190, times the change in temperature. So 15 to 100 degrees, that's 85 degrees of change, plus 0.5 kilograms of water that has to evaporate, times the latent heat, which is 2256 times 10 to the 3. So that's going to give you 1,306,075 joules. Okay, so that's the total amount of energy required to make the liquid go from 15 degrees to 100 degrees, and then to turn all the liquid into vapor. Okay, so we've got that number. Now I'm going to erase all of this. So what we're after is the time, right? So we have the power. Power is equal to energy over time. We've just figured out what the energy is going to be, so we're just going to rearrange this equation for T. T is equal to E over power. Our energy is 1,306,075 joules, and our power is 750 watts. Right. So if you do that, they'll give you 1,741 seconds. So that'll be your time in seconds. But they want the answer in minutes. So you have to divide that by 60 in order to get minutes. And that will give you 29.0 minutes, which is your answer. Okay, so our next one, we have a cylinder containing a diatomic gas with a volume of 0.5 meters cubed and a pressure of 200 kilopascals, a temperature of 20 degrees Celsius. We want to find out the number of molecules of gas in the cylinder. So because we want to find out the number of molecules of gas, that's going to be the symbol that represents the number of molecules, not the number of moles. So little n, remember, is number of moles, whereas capital N, big N, is going to be the number of molecules. Molecules or atoms. Okay? And yeah. So, and the number of molecules, oh no, you don't need to know that. Okay, so yeah, so then we're going to use this equation here. PV is equal to capital N times K times T. Okay, PV equals NKT. That's pretty similar to PV equals nRT. Okay, and now we're using K. So K is equal to 1.38 times 10 to the negative 23. Okay, so what we want is the number of molecules. So we're going to rearrange this equation for N. N is equal to PV over KT. So that's Our pressure is 200 kilopascals, so 200 times 10 to the 3 times our volume, which is 0.5, over our K, which is 1.38, times 10 to the negative 23, times our temperature. So here we have to have it in Kelvin. So that's going to be 293.15. And that should give you 2.47 times 10 to the power of 25, which rounds to 2.5 times 10 to the 25. Number 10, we have a gas cylinder with a volume of 10 meters cubed, and it contains a mixture of gases at a temperature of 20 degrees Celsius. The cylinder contains 1 mole of diatomic oxygen and 2 moles of monatomic helium. So we want to find the total thermal energy contained in the gases in the cylinder, and that's in kilojoules. Okay, so total thermal energy or internal energy, because it's a gas. So that's the symbol U. So the U total will be equal to the total thermal energy of the diatomic oxygen plus the total thermal energy of the monatomic helium. Now we have to calculate them separately because one of them is diatomic and the other one is monatomic, so we can't just add them together. Okay, so let's calculate the energy of the diatomic oxygen first. So that's going to be 5 over 2 multiplied by the number of moles multiplied by R multiplied by T, the temperature. So the number of moles is 1. So you wouldn't have to put that in there because 1 times anything is just itself. But I've just put it in there for clarity. 8.3 is R multiplied by our temperature, and it's got to be in Kelvin. So that's going to be 20 plus 273.15, which is 293.15. And that would give you 6,083 joules. So I've just rounded it up to the nearest single digit, nearest one. So next, the total internal energy of helium is going to be 3 over 2 because it's monatomic. And again, it's going to be times N times R times T. So I'll get straight into it. That's 2 moles of helium. R is 8.3. And the temperature, again, is 293.15. So the total internal energy is going to be 7,299 joules. And that will be... So the U total will be those two added together, so 6,083 plus 7,299, which equals 82 joules. Okay, so if you divide that by 1,000 to turn that into kilojoules, you'll get 13.4 kilojoules. Okay? All right. Don't have a whiteboard eraser, so my sleeve will have to do. I'll just wash that later. It's dedication to the job. I've got a sealed rigid container of fixed volume containing dry air, which has an internal pressure of 100 kilopascals at 25 degrees Celsius. What's the pressure in kilopascals in this container when it is cooled to minus 5 degrees Celsius? So we have a change in conditions, so our temperature is being reduced. We've got a fixed volume. So if we have a fixed volume, that means that the volume doesn't change. So the volume before equals the volume after. V1 equals V2. So we're going to use our equation. P1 times V1 over T1 is equal to P2 times V2 over T2. Okay, and since V1 equals V2, we don't need that in there, and we're after the new pressure, so we're after P2. So P2 will equal P1 times T2 over T1. Okay, so pressure 1 was 100 kilopascals, which is, so you need to convert that into pascals. It's very important. Lots of people forget this step. So that's times 10 to the 3 multiplied by temperature 2, which has to be in Kelvin. So of course add 273.15, so 298.15 Kelvin. And the original temperature T1 was, oops, sorry, my bad. So this here should be T2, the final temperature, which is negative 5 degrees Celsius. So that's going to be 268.15. Okay, and the original temperature was 298.15. My bad. So we're going to get an answer of 89,938 pascals, which divide by 1,000 to get kilo, rounds to 90 kilopascals. Okay, simple. All right, next question. Got a rigid cylinder with a volume of 7.5 times 10 to the negative 3 meters cubed, which contains an ideal monatomic gas at a pressure of 101 kilopascals. What's the total thermal energy of the gas in the cylinder in kilojoules? So we have the volume. Volume is equal to 7.5 times 10 to the negative 3 meters cubed, and our pressure is equal to 101 times 10 to the positive 3 pascals. Right, so we've converted kilopascals into pascals, and we want to find out what the total thermal energy is. Right, total internal or thermal energy. So our equation for thermal energy is, since it's monatomic, it would be 3 over 2 times N times R times T, right? But we don't have N, and we also don't have T. But you should remember that you have this equation here, which is PV is equal to nRT, right? So what that means is that we can replace this part of the equation, nRT, with pressure volume. Okay, so that's what we're going to do, because those are the variables that we do have. So now U is equal to 3 over 2 times PV. So 3 over 2 times 101 times 10 to the 3 times our volume, 7.5 times 10 to the negative 3. Okay, so that will give you a total thermal energy of 1,136 joules. Again, divide by 1,000 to get 1.14 kilojoules. Okay, so that's it for today. Thank you very much.